Good day, everyone. Today, we are going to explore the wonders of Earth's mechanism. I'm Sir Janus Ada, and I'll be your guide for today as we discover the wonders of plate movements and its impact to present-day Earth. For today's topic, here are our session objectives. First, describe the possible causes of plate movements and recognize the process of convection current in the mantle. First, let us explore Lesson 1 on mantle convection. Can you still recall who was the proponent of the continental drift theory? It was Alfred Wegener. He was a key figure in changing ideas about the Earth's surface. In 1912, he proposed that all the continents were once joined in a single supercontinent called Pangaea. Unfortunately, due to the technological limitations at that time, his theory was not accepted. He proposed or suggested that Pangaea began to break about 200 million years ago, and pieces drifted apart to form the present-day continents. Can you still recall the evidences put forward by Alfred Wegener to support his theory of plate movements, or the continental drift theory? The first evidence presented by Alfred Wegener is known as the Geological Fit Evidence, wherein it shows the matching of large-scale geological features on different continents. This evidence notes that the coastline of South America and West Africa seem to match up, much like a jigsaw puzzle. Another evidence that supports continental drift theory is that same fossils were found on different continents. And when we talk about fossils, these are the remains of living things that lived long ago. There are various examples of fossils found on separate continents, wherein this would have been impossible if the continents have been separated by vast oceans and seas years and years ago, such as the Glossopteris fossils, the Signonatus, and the Mesosaurus. The next set of evidence that supports continental drift theory is the rock evidence, or using mountain ranges. As you can see, mountain ranges separated by vast distances of oceans share the same characteristics, which goes to show that these mountain ranges once are next to each other. After mountain ranges, the next set of evidence for continental drift theory is what you call as glacial scars. So what are glacial scars? These are traces of glaciers found in many tropical regions of Earth. When continents drifted apart, these glaciers melted away, but however, it leaves track or scouring and polishing of rock surfaces. As you can see here, when the ice melted, it left imprints or scratches on the rock, which goes to show that even though these continents now are located near the equator, however, it still has traces of glaciers, which goes to show that this one or these continents share the same locations. The next set of evidence solves the mystery why tropical plants are located in Antarctica, as well as coal deposits which has been located in temperate and polar regions, wherein it is impossible since coal is formed in tropical regions. Climate evidence explains that Continents are once joined together. That is why tropical plant remains found in Antarctica as well as glacial deposits in Africa, South America, India, and Australia, because this existed during the same time at the same locations. Here's a quick look on the proposed theory of Alfred Wegener. As you can see, from Pangaea down to the modern locations of each continents. In order for us to fully understand convection in the mantle, it would be best to discuss the key concepts or to boost our vocabulary on the topic. The first key concept is the mantle. Mantle is described as a layer beneath where the less dense hot molten material rises and sinks. So it's a part of the Earth's layer. The next key concept that we would be dealing is what you call as the Asthenosphere. It is described as a soft, weak, and plastic-like layer which is the upper part of the mantle. This is where lithospheric plates float and move. So if the mantle is here, the asthenosphere is located here just below the crust. One common misconception is that the asthenosphere is a liquid. The correct term for the asthenosphere is that it would be a viscoelastic solid, which is comparable to a rubber being melted. Magma refers to hot molten rocks formed beneath the Earth's surface. By the way, do you know the difference between magma and lava? Actually, they are made up of the same material. The only difference is that when magma is spewed out and being released to the Earth's surface, then the correct term now would be lava. Another key concept is the convection current. It is important to note that the convection current facilitates the movement of the lithospheric plates. The next key concept that we would be dealing is the Earth's core. Core is described as the innermost layer of the Earth, which generates heat to the mantle. Another plates can also be called as tectonic plates, which refers to a massive, irregularly shaped slab of solid rock, generally composed of both continental and oceanic lithosphere. By the way, can you still recall the difference between oceanic crust and continental crust? When you talk about oceanic crust, this refers to lithospheric plates which are located underneath the ocean. And of course, those lithospheric plates which are located above it are known as continental crust. Next key term that we will talk about is known as slab pull and ridge push. So when you talk about slab pull, this refers to the pull of gravity on a plate that is being subducted. On the other hand, when we talk about ridge push, this is when magma pushes the plates apart. Now, to illustrate the main difference between the two, kindly take a look at the figure. Ridge push are located generally where the hot molten material rises. This is where the tectonic plates are being separated and at the same time, new crusts are being formed. On the other hand, slab pull It is located on subduction zones. Now that we have already unlocked the key concepts, we would now proceed with the simulation of plate tectonic movements among boundaries. Imagine your hands represents the tectonic plates. Each movement represents a type of process that happens along the boundaries. Are you ready? So you are going to put your hands together like what is shown on the video. Slowly move it away from each other. You are already simulating the movement of a divergent boundary wherein the plates are moving away. For the next simulation, position your hands based on what is shown on the video. Slowly move it toward each other. You are now simulating the convergent boundary between two oceanic plates. Next, position your hands again based on what is shown on the video. Slowly move it toward each other. You are now simulating the convergent boundary between continental and oceanic plates. The clenched fist represents the continental plate and the open palm represents the oceanic plate. Since it is denser, the oceanic plate subducts under the continental plate. For the next simulation, this is between two continental plates. So position your hands again based on what is shown on the video and slowly move it toward each other. Again, you are simulating the convergent boundary between two continental plates. The clenched fist represents the continental plates. Since both plates are made up of the same materials, no subduction happens. Instead, what is formed is known as collision zone, wherein the mountain formation takes place because of the uplift. For the final simulation, position your hands again as what is shown in the video. Then slowly move your other hand forward while your other hand moves backward. You are already simulating the movement of the strike slip or the transform boundary. This time, let us discover the geologic processes that would take place among these boundaries. The divergent boundaries, the geologic processes that happens here is that new crust is being generated as the plates are being pulled apart, and it also produces ocean ridges if it occurs underneath the ocean, whereas on land it would produce continental reefs such as this one. It could also produce earthquakes which are shallow and small. The next type of boundary is known as convergent boundaries, and as we all know, there are three processes that could take place between a convergent boundaries, specifically for the ocean-to-ocean convergence, continental-to-continental convergence, and for the ocean-to-continental convergence. It is important to note that what happens in convergent boundaries is that the denser plate subducts and two continental plates crunch together to form high mountains. For an oceanic to oceanic plate convergence, this is what would happen. It can produce a volcanic island such as the formation of Hawaii. It may also cause tsunami, and the location wherein one of the plates subducts, it would produce ocean trenches. For the second, in ocean and a continental plate convergence. For this type of convergent boundary, it may produce the following geologic events. Of course, it can produce earthquakes. It may also produce volcanic arcs, also trenches on the subduction zones, and just like the ocean-to-ocean convergence, it may also trigger tsunamis. Last is between continental to continental convergence. The geologic events that would take place for this type of convergence is that there are shallow earthquakes and the formation of mountain ranges. So this type of plate convergence gives rise to the formation of the Himalayan mountain range, wherein Mount Everest, the highest peak, is included. The last type of convergence is known or between transform boundaries. For this one, the lithosphere is neither produced nor destroyed because the plates slide horizontally past each other. One famous example of a transform boundary is the San Andreas fault line. You might be wondering what makes the massive lithospheric plates move. Well, hold on to your seats, for we are about to find out. The whole process starts with radioactive decay, wherein the decomposition of radioactive elements causes the heat in the interior part of the Earth. About 50% of the heat given off by the Earth is generated by the radioactive decay of elements such as uranium, thorium, and their decay products. From radioactive decay, the heat moves now to the core. There are three main sources of heat in the deep Earth. First one would be heat when the planet is formed and accreted, which has not yet been lost, and of course, from frictional heating caused by denser core material sinking to the center of the planet. And for the third one, the heat from the decay of radioactive elements. From this heat, it now slowly rises to the mantle and creates what is now known as the convection current. So the heat from the core slowly rises to the mantle and creates the current. Remember that hot material rises while cooler material sinks. This process is repeated as long as there is the supply of heat, giving way for the creation of an event known as convection current. The fourth stage is the wedge push and slab pull. The convection current created due to heat generated from the Earth causes the lithospheric plates to move in the asthenosphere due to the rising and sinking of materials. Take note that the area where the magma rises creates wedge push. It is also the area where the new crust is formed. On the other hand, the areas where two plates collide, that is where slab pull would take place. And of course, with the aid of gravity, the denser material subducts in an area known as the subduction zone. And of course, the process repeats as a cycle. The rising of hot material cools down in a certain area, hence it becomes denser than the cool dense material and it would sink. That creates the convection cell with hot rising currents and cool sinking currents are regularly repeated and become a cycle. This time, let's test how much you have learned by taking on this challenge. For the first challenge, you will be given 5 seconds to unjumble the word based on the clue given. So are you ready? First clue. It is a layer beneath where the less dense hot molten material rises and sinks. The correct answer is mantle. Did you write mantle? If yes, very good. You got it right. How about the second item? It is a soft, weak, and plastic-like layer, the upper part of the mantle where lithospheric plates float and move. Time starts now. The correct answer would be Asthenosphere. Are you ready for the third item? For the third item, this one refers to hot molten rocks formed beneath the Earth's surface. So, another 5 seconds. Correct answer is magma. Did you get it right? For the fourth item refers to what facilitates the movement of the lithospheric plates. The correct answer would be convection current. On to the final item. Now for the final item, it refers to the innermost layer of the Earth, which generates heat to the mantle. 5 seconds. The correct answer would be core. Did you get it right? Congratulations! This time, let's test your knowledge on the process of convection current. What you will do is that you are going to arrange the following events in the mantle convection process. You are going to use the numbers 1 to 5, 1 denoting the first process, and of course 5 the final process. So you will be given only 30 seconds to arrange the items. Are you ready? So here are the correct responses. Okay, so congratulations, you accomplished the task for today. A well-deserved applause for a job well done. A bright and brilliant mind always seeks learning and knowledge. And so, in preparation for tomorrow's lesson, I'd like you to investigate just like what Sir Alfred Wegener did. Find other evidence that support the continental drift theory. Specifically, you are going to do a research, so you may refer to books and the internet. You may also scan Module 5 on seafloor spreading. Tomorrow, we will discuss another theory that will try to explain the world we know today. I hope you gained a lot of learnings today. I will see you again tomorrow for another fun-filled day of discussion and exploration. This is Sir Janus saying thank you and God bless.